Okay, hello. We are back on Friday night or Saturday morning or something. I assigned the homework for the weekend due on Monday, and the homework was to watch this big video, which was going over a previous homework, learning some new things, and then finishing up going over that homework. Okay, and then, we're sort of didn't really learn anything new, really like new in class actually on Thursday and Friday, and nothing sort of absolutely new happened in that video either in terms of we didn't make any progress through the textbook. So the homework was just 4 problems, but they were hard, or at least 3 of the 4 were hard. And a lot of them were just kind of new versions of problems that we already did. So, all right, let's go. 47 is supposed to take 1 second. Here we have a function h. The independent variable is s for whatever reason, and it's s to the 4/5 minus s to the 2/3. So this is just practice on you using the general power rule. So what is the derivative of s to the 4/5? Well, you apply the power rule, and it's 4/5 s to the negative 1/5 minus 2/3 s to the negative 1/3. And you either leave it like that, or if you want to be cool, you can write this as 4 over 5 times the 5th root of s minus 2 over 3 times the cube root of s, and maybe that's worth writing, maybe not. Okay, that was number 47. Good, 1 down, 3 to go. 65 was almost exactly like 63, this problem that we did in class on Thursday and Friday. What was the problem? Well, they give you a function, but in this case the function is k over x, but I don't know what k is, and in fact the goal of the problem is to find k. What do I know about this function? Well, I know that this particular line, y equals negative 3/4 x plus 3, is tangent to the graph of this function. Okay, I believe that's just what they say. Yep. So, great. Great. Well, we begin. Well, I don't know where to begin, actually, because, once again, I don't know whether k is positive or negative. And the idea is, if k is positive, then k over x kind of looks like a 1 over x function. Well, it's going to look like this. And if k is negative, so this is the, maybe I'll just say it like this. This is the k is positive case. If k is negative, then it looks like this. So not knowing what k is means I don't really want to start there. So maybe I'll start with graphing the line, and then maybe I can figure out whether k is positive or negative. Okay, so here's, I haven't done this problem recently, so I forget what a good scale is or whatever, but I'll sort of just figure it out. If this is the line, negative 3/4 x, then here's 3, and if the slope is negative 3/4, then I guess I'm going to go down 3 over 4. So I got something that looks like that. That's my line. And, well, okay, I now see that it's just impossible for this line. This line is kind of inconsistent with k being negative. So I think k must be positive. I still don't know what k is, but I think I'm ready to draw in the curve. I don't know exactly what it looks like, but it's going to be some sort of thing that's like this. So it's going to come up, and then, I don't know, somewhere around here or whatever, it's going to do that. And then there'll be more of it over here, but I don't think that part over there is going to play any role. Okay, great. I have a picture now, so I can begin sort of thinking, what do I know and what do I not know? I kind of don't know anything. I know that the slope of this tangent line is negative 3/4. That's kind of nice. And I know I have this curve. I guess crucially, what I don't know is what this point is. So let me give it a name so that I may reason about it. And here we sort of repeat the logic from the previous class. This, if this x value is a, the y value, because it's a point on the curve k over x, is k over a. But like also this y value is negative 3/4 a plus 3. In other words, this point where the line is tangent to the curve is a point that is on both the line and the curve. And so one thing that's true about this point A is that negative 3/4 a plus 3 has to equal k over a. And of course, the other thing that must be true about it, if this really is the tangent line, then the derivative of the function at a must equal the slope of the tangent line, which is negative 3/4. And so I take this function, I write it in derivative-friendly form, so k over x, that's like x to the negative 1. So this is kx to the negative 1. This just makes it easier for me to use the power rule, and I use the power rule, what do I get? Negative kx to the negative 2. Okay. And so what is this in a kind of algebra-friendly way? This is just negative k over x squared. And this is the rule in general for the derivative of this function, but what is the derivative at a? Well, the derivative at a is negative k over a squared. And so there are two facts about this function that I know. I know that the y values are equal at x equals a, and I know that the slopes are equal at x equals a. So, on the one hand, the derivative of this line is negative 3/4, but on the other hand, well, maybe that's, I think I've made my point. I guess I can just go right for it. What's true? What's true is that negative k over a squared is negative 3/4. The slopes are equal, and the y values are equal. Okay. I guess really that's it. I don't think there's anything sort of deeper going on. Now this just becomes kind of an algebra problem. Can we solve this system of equations, two equations and two variables? So I guess, we're just going to do that now. Let's go. Let's see what seems like the simplest way to do this. Well, in the second equation, I can cross multiply, I guess, and the negatives cancel as well. So I get 3a squared equals 4k. And in this first equation, I kind of just don't want any fractions, so I'm going to multiply through by 4a. Multiplying through by 4a is going to kill all the fractions. So if I multiply this by 4a, the 4 cancels and I get negative 3a squared. If I multiply this by 4a, I get 12a, and I multiply this by 4a, I just get 4k. Alright, well, that seemed to be a very good method for simplifying this system. All my fractions are gone, and now I can just set these equal to each other and solve this equation. So what do I get? I get that 3a squared is negative 3a squared plus 12a, and okay, I mean, I don't know. So what do I get here? 6a squared minus 12a equals 0. I'm being kind of careful about moving everything over to one side so I don't lose any solutions. But of course, so what is this? A minus 2. But of course, a equals 0 is like impossible, right? So the only solution to this is a equals 2. So this is actually an easier problem than the one from last time, I think, because I have only one solution. The solution is that a is 2. And, okay, let's just see if it all makes sense. When a is 2, then what's k? Well, looking, I suppose, here, if a is 2, then k is just 3. So a is 2, k is 3, and I think that was just the solution to the problem, so we're just done. We can double check it for sort of understanding. It means then that my function is the function 3 over x, and 2 is the place where it's all happening. Let's see if that is kind of consistent with everything we've done. So I'm kind of just checking my work, basically. If I plug in 2, I get 3 halves. Okay. is 3/2 on the line y equals -3/4 x plus 3? I suppose so, because, well, I don't know. So -3/4 times, I mean, I could have made a mistake. Sorry, that was actually the wrong thing to even be talking about. This point, I am learning, is the point, if I've done this all correctly, 2 comma 3/2. And let's see if that makes sense. So when I plug 2 into this line, I indeed, what do I get? I get -3/2 and 3, so that is 3/2. So that part's checking out, that the point 2 comma 3/2 is on the line and also on the function 3/x. And then what do? Finally, I guess I can just plug, if the function is 3/x, then the derivative of that function is, in general, -3x to the -2, or just -3/x squared. And then what's the derivative at 2 specifically? Well, it's -3/4. And indeed, the slope of the tangent line is -3/4. So this is all making sense, and it's all perfect, and sort of there it is. Okay, good. 2 more, 78 and 73. I'll just keep the video running, I guess. 78 is a problem that's almost exactly like what we did in class. No, I think I didn't do this one in class. I did this one on the video, but it's exactly like a previous homework problem. So my experience is a lot of people don't get this on the first try. So if you were one of those people that didn't get number 77, you know, he was kind of like your second chance or something. So what is 78? It gives you a function, f of x equals 2/x, and it gives you a point that's not on that function. The point is 5 comma 0. And the directions are, find the tangent line which goes through point 5 comma 0 and is tangent to the graph of this function. So, okay, this is another problem that tests your sort of flexibility and understanding of differentiation. So let's graph the function 2/x. Well, I plug in 1, I get back 2, I plug in 2, I get back 1. So I got something that looks like that. Cha. And then I have some stuff over here too that might be relevant. -2, -1, -1, -2. So this is me just sketching a nice curve. Okay, great. Well, then there's this point, 5 comma 0, which is of course not on the function, so 3, 4, 5. So I got this point here, 5 comma 0. And now the directions say, say find the tangent line which is going through the point 5 comma 0 and is tangent to the graph of this function. So, alright, let's see. I think my picture is telling me that something like this is going to be one of them, maybe. But there might even be another one. And so, I don't know. Maybe I'll just draw one and see what the algebra tells me. So, okay, what have I done? I've just sort of taken a big stick, and I still have forgotten to prepare a stick. Here we go. This is a, here's a firework. Got a bunch of fireworks here. This is like a bottle rocket, so that's kind of like a stick. What have I done? I've glued sort of one end of the stick to the point 5 comma 0, and thinking of this function as kind of like a boulder, I just swing it up until it bumps into the function. That's kind of like what the tangent line is. Okay, so having done that, now I'm ready to start the problem. What are my observations? Well, one observation is I don't know anything really at this moment. I don't know what this point is, and I also don't know what the slope of the line is. So I don't know anything. So, all right, let me call this point A. And if I call this point A, then what's the y-coordinate? Well, the y-coordinate is like 2 over A. So that's A comma 2 over A. All right, and I don't know the slope of the line, but I can determine the slope of the line using calculus, because this function is just the function 2x to the negative 1, and so its derivative is, via the power rule, negative 2x to the negative 2, so that's negative 2 over x squared. And since that's the rule in general, then if I want to know the derivative at a, I just plug in a, I get negative 2 over a squared. Okay, so on the one hand, the slope of this line is negative 2 over a squared. But on the other hand, man, I don't remember, no memory of doing this problem. On the other hand, the slope of this blue line can be calculated by looking at this little triangle here. Now I wish I had made this picture a little bit bigger, but here I do have like a triangle, and I have basically 2 points, both of which are on this blue line. One of the points is 5, 0, and the other point is a comma 2 over a. And so I can, just calculate the slope of the line that way, right? What is this, this y-coordinate here is like 2 over a, and this x-coordinate here is 5 minus a. And so, using that formula, or using that way of thinking about this line, the slope of this line can be expressed, again, in a different way, in terms of a. What is it? It's down 2 over a, so negative 2 over a, over 5 minus a. Now, of course, I can maybe just multiply the top and bottom by negative 1. So it's like 2 over a minus 5. And even I can write that as 2 over, a minus 5. And, alright, so I think that's it. That's the thinking for this problem is kind of over. What must be true about this point A that I'm trying to find? Well, it must be true that the slope of this line, as calculated with these 2 points, 2 over a minus 5, must be equal to negative 2 over a squared. Yeah, I guess that's it. Alright, so let's just solve this quadratic equation. What do I get? The 2's cancel, so I get a squared equals negative a minus 5. Assuming I did that right, sure I did. A squared, yep. So that's a squared equals negative a squared plus 5a. And what do I get? 2a squared minus 5a equals 0. So factoring out an a, again I'm being sort of, careful, but you might even say overly careful about this, because I didn't want to lose the solution a equals 0, but once again the a equals 0 solution is nonsense. So there's only one real solution, which is 5 halves. And so I kind of thought that there wasn't going to be another, I'm glad I didn't try to draw it in there, because my feeling about the geometry of this shape was that there just wasn't going to be another tangent line. So yeah, good. A is 5 halves. Does that look about right? Well, on my picture it looks like about 3.5, but who said my picture was accurate? It probably just wasn't so accurate. It's not outrageous either, though. Let's see. If this is the case, then what should we do to check it? Well, I can just kind of plug in 5 halves to my function. What do I get? 2 over 5 halves. So that's 4/5. Great. Great. Is it true then that, so what's the slope of this line? Well, it's delta y over delta x. If that point is 4/5, then that means that what I just learned was that this is 5 halves comma 4/5, this point. Let's see if that makes sense. Well, I'm going to go down 4/5. So the change in y is negative 4/5, and the change in x is 5 minus 5 halves, just like another 5 halves. So I'm just doing some algebra 1 here. Well, it's really geometry, and just looking at those 2 points and finding the slope. What do I get? Negative 8/25. That's a little bit surprising, but maybe that's just the right answer. Okay, so the slope of this line is apparently negative 8/25. Let's see if that matches up with my calculus. Well, I've already calculated that the derivative of this function is negative 2 over x squared. And so if I plug 5 halves in, then I get negative 2 over 25/4. And indeed, that's negative 8/25. So it just is true that this point, 5 halves, comma 4/5, on this curve, 2 over x, has derivative equal to negative 8/25. And it's all sort of checking out, so I guess I'm done. What am I supposed to be doing? Find an equation of the tangent line. So the final answer to this problem would be y minus 4/5 equals negative 8/25 x minus 5 halves. That is the slope of the tangent line. But really, it's all about first finding the point of tangency. And to find the point of tangency, we temporarily name it something and reason about it indirectly. Both that the slope of this line can be calculated via just rise over run, and then also that the slope of the line can be calculated via calculus formulas. Okay, good. Back in 1 minute to do number 73, which is very hard. Okay, we are back for number 73, and this is in many ways just kind of a follow-up to the problems that we've just been doing. It's just harder. So it's like, I think it's significantly harder. Let's go. The function, well, what does the problem say? It gives you these two curves, parabolas, and says, sketch the graphs, sketch the two lines, find the equations of the two lines that are tangent to both graphs. Yikes. Okay, well, first let's make a picture. Kind of a big picture, although space on this board is going to be kind of at a premium. I've decided to label these functions f and g, just so I can refer to them individually. Of course I can graph x squared. If I'm going to graph negative x squared plus 6x minus 5, let me do a little algebra 1 here to get a kind of handle on this. Yeah, what does it look like? Well, it's negative x squared minus 6x plus 5. I think that factors into x minus 5, x minus 1. So that's really like my g function. Okay, so maybe over here or something, I will now graph this. And to decide what to do. I guess I'll do it over here. So here we go. Yeah. So first, y equals x squared. So trying to be a little bit accurate and stuff. 2, I'm going to be up at 4. So there we go. So something like that. All right, whatever. Good enough. And then, so that's f. I'm wondering if I should have made this picture even bigger. Well, too late. Then I have my function g. G is going to be an upside down parabola with roots at 1 and 5. So 2, 3, 4, 5. And okay, if the roots are at 1 and 5, then the vertex will be at x equals 3. If I put 3 in here, I get 2 times negative 2 times a negative, so that's 4. So I could have completed the square, I guess, but you know, instead I get this vertex up here, 3 comma, or not vertex, yeah, vertex of the parabola is at 3, 4, and then let's see, what else? I guess I'm going to have a point even like 2, 3, yeah. So these guys are pretty close to each other, and right, because if I plug in 2, I'm going to, yeah, and because that's just how parabolas work. So let's see, if I can draw this, it looks like this. Not so happy with this picture. to be totally honest, but I guess it will have to do. Something like that. Alright, so here I have these two functions. And, okay, they're kind of just like, think of these two functions as like boulders. Here are two giant boulders. And what we are going to do is kind of go climbing inside these boulders. Wait, I fear that this... sorry, I'm going to waste a minute because I just think if this picture's too small, it's just all going to be a failure. Sorry, considering redoing the video, but I think I can redo this in like 1 minute. So let's redo it in 1 minute, but big. 1, 2, 3, 4, 5. 1, 2, 3, 4. So what's going on? Y equals x squared. That's f. And then the g function, 1 and 5, I get 3, 4, 2, 3. This is going to be just going to be better. So, something like that. Okay, that's looking fine. they still seem to be extremely close together, but okay. Great. Great. What am I supposed to be doing again? I'm supposed to be finding the equations of the lines which are tangent to both of these graphs. Okay, so this is now suddenly really hard because I have two functions. And what am I looking for? I'm looking for a line which is tangent to both of them. So it needs to be, it needs to have the property that it's touching one function and also touching the other. So it's like a mutual tangent line. And if you sort of think about it, what's happening here, if you think of these things as two big boulders, this is what I was just saying, then it's almost as like you're sort of stuck between these two boulders, like some kind of, well, okay. So I have one line, you can sort of see it, which is going to come up, shoop, so sort of stick, a long stick. I could even go out one more if necessary. Take this big stick and then just like jiggle it or whatever. And if you jiggle it, then I think you will see that if you jiggle it one way, it's going to go and it's going to get stuck touching the F boulder on the left and the G boulder on the right. And if you wiggle it the other direction, then you're going to get another line, a different tangent line, which is touching the G boulder kind of down here and the F boulder kind of up here. And so there are these two tangent lines, each of which is tangent to both of these functions, but at two different places. And I think this is what actually makes this problem so hard. So let me draw in one of these. One of them kind of looks like this. Shot. Okay, and so I have these 2 points here. And this is just like the previous problems we've been doing, but now there are sort of two unknowns. So what do I know about this line? I know that this line is touching the point F. Sorry, this line is tangent to the F function and also tangent to the G function. But of course they're tangent in sort of two totally different places. And alright, without confusing my picture too much, I am already aware that if I were to just kind of take this whole blue line and go, then it's going to get stuck between these two boulders in a different way. So there really are going to be two solutions to this problem. I already see in advance. In fact, the book just says there are two solutions. So I don't know what the slope of this line is. I don't know where this line is tangent to the G function. I also don't know where this line is tangent to the F function. So I'm going to do the thing I did before, which is to give this point a name. Let's call it A. Well, if this is A, then the y coordinate is A squared. Chop, chop. And then I'm going to call this point B. And if this is B, then the y coordinate is negative b squared plus 6b minus 5. Chop. And so, okay, I now don't know either of these two numbers, A and B. and I have to sort of find both of them. Okay, and I basically defined B as the point of tangency of the line to the G function, and A is the point of tangency of the line to the A function. Okay, having done that, I now claim that I can find the slope of the tangent line to this curve in 3 different ways. One way is by just computing the change in y over change in x for the 2 points that I have on this blue line. So what is the change in y? Well, the change in y is going to be negative b squared plus 6b minus 5 minus a squared. And the change in x is just b minus a. So on the one hand, I have that the slope of this line is just negative b squared plus 6b minus 5 minus a squared over b minus a. But I can also use calculus because this is the tangent line. So let's take my f function. What can I say about this f function? Well, it's x squared. So what's its derivative? Well, its derivative therefore is 2x, and that's the derivative function in general. But the only thing I care about is the derivative at a. And what is f prime of a? It's 2a. So I also know that the slope of this line is 2a. Cha-cha. And I also know that that this is the tangent line to the graph of g. So I also know that the derivative of g at point B will have the same slope as these other two. Okay, so this is really forcing you in this problem to have a good conception of the difference between a derivative function and the derivative at a point. So I can easily, just by following the rule, my function is negative x squared plus 6x plus 5. It's easy for me to just find the derivative of this function. What is it? Well, just using the method for differentiating polynomials, I get negative 2x plus 6. So that's the derivative function in general, but it's specifically the derivative at b that I want, and that's negative 2b plus 6. And so here, I have now kind of like one big super equation or something like that. And yeah, so is this enough to find A and B? Yeah, it is, because this is a little bit hard to kind of explain, but if you take the functions sort of 2 at a time, then it's really like you have from these 3 equations, sort of from these 3 expressions that are all equal to each other, you really have 2 equations in 2 variables, and therefore that should be sufficient to solve a system of 2 equations in 2 variables. Alright, so I think the hardest part now, besides the setup and the picture and the understanding, which we just did, the algebra is also maybe a little bit hard, so let's go. What do I know? Well, I'll now start to kind of solve this. So if I know that 2a is negative 2b plus 6, then I guess the easiest thing to do is just solve for a. A is, therefore, by dividing both sides by 2, a is just 3 minus b. Alright, so if a is just 3 minus b, then I propose to substitute that into the so-called other equation, which is just the 2 left pieces. Okay, so let's do that now. I guess that's kind of the same thing as setting them equal. Now that I think about it, it's the same thing as just setting these 2 equal to each other. So let's just let's do that. So okay, so what do I get? I get negative b squared plus 6b minus 5 minus, and now in place of a squared, I write 3 minus b squared. And all of that over b minus a. Well, b minus a will just be, maybe I'll even just write it as b minus, what's a? It's 3 minus b. And this whole thing equals negative 2b plus 6. Alright, so that's a little bit tricky. I sort of well, I guess what I did is I just used the fact that used these two expressions to write A in terms of B, and then yeah, I think it's clear what I did. Okay, so I have a single equation now in B. Can I solve this? I don't know. Let's go. What do I end up with here? This is like negative b squared plus 6b minus 5 minus, squaring this binomial, minus 9. That's minus 6b in there, so that becomes plus 6b minus b squared. All over, this is just 2b minus 3. Because b minus 3 and then plus another b. So that's 2b minus 3 equals negative 2b plus 6. Alright, I feel like this is the best way, but I'm having some space problems, but I think this is pretty clear so far. Okay, can I simplify this left-hand side at all? Yeah, I guess so, right? Minus plus, yeah, I haven't made a mistake or anything yet. I don't think so. So let's go. What do I end up with? Negative 2b squared is that numerator. Negative 2b squared plus 12b. And then what is that? Minus 14 equals, yep, negative 2b squared plus 12b minus 14 equals, and then when I multiply these two together, I am going to get something. I don't know, let's just do it. Negative 4b squared plus 12b plus another 6b. I hope I don't mess this up. Minus 18. I haven't done this problem in a while, but maybe it's just okay. Let's see. So, yeah, alright, so negative 2b squared plus 12b minus 14 equals negative 4b squared plus 30b minus 18. I can divide by 2, but maybe first I'll just kind of get going here. Adding this over here gives me 2b squared and then minus 18b. And adding 18 gives me plus 4. Man, I hope this is right. So dividing by 2, b squared minus 9b plus 2. That is very disturbing. Oh man, hold on. Give me 1 second to find my error. Negative b squared plus 6b minus 5. So that's minus a squared, sure, all over b minus a, 2a, negative 2b plus 6, good. A is certainly 3 minus b, fact, minus, so that's b squared minus 6b plus 6b minus 6, yeah. I don't see any mistakes yet. Plus b, 2b minus 3, 2b plus 6, negative 4b squared plus 12b plus another 6b. Oh, that's the mistake. I sort of did something dumb here. Negative 4b squared plus 12b, but then plus another 6b. So I kind of like did it the slow way and then the fast way at the same time. So that should be 18b. So that should be minus 6b. And now this is minus 3b. Woo! Okay, that wasn't too bad. Yep. So what is this? This is b minus 2, b minus 1. And what do I find? That there are two options for b. b equals 1 and b equals 2. Alright, well, cramming this in somehow, I was hoping I would have more room. I guess I'll split it up into two sort of cases. There's case 1 and there's case 2. What's case 1? Case 1 is when b equals 2, which is the case that my picture represents. So if b equals 2, then first of all, what's a? Well, a is 3 minus b, so if b is 2, then a is 1. And if a is 1, then I can tell you what this point is on the f function, f of 1 is just 1. And so since f of 1 is 1, we have this point 1 comma 1 on the graph of f, which is exactly what this blue dot looks a lot like. I'm not going to bother labeling it, but that is 1, 1 according to my math. And then, of course, g of 2 is, we already plugged 2 into g. We can just do it again really quick, and we get 3. And so I have this point 2 comma 3. So everything is just like looking good, right? There's this point 1, 1. There's this point 2 comma 3 on g. If that's the case, maybe I will just in purple or something, I will say that that's 1, 1, and that's 2 comma 3. Then what's the slope of the line? Well, I'm going to go up 2 over 1. So the slope of this blue line is therefore 2. According to just doing a simple rise over run algebra 1 calculation. But it's also true that if I take f prime of 1, using my formula for f prime, which is just 2x, I get 2. And it's also true that g prime of 2 is, following my formula for g prime, is also 2. And so everything is just checking out, and it turns out that we have just this line with slope 2 going through 1, 1 and 2 comma 3, and everything is like perfect. So what's one answer to this question? Is the line with slope 2 going through 1, 1. So it's y minus 1 equals 2 x minus 1. And maybe I can even say that even more simply as minus 2, y equals 2x minus 1. Just double checking that, but of course that's right. Good. So first solution, y equals 2x minus 1. But I'm already convinced that there's this kind of other solution, so it just falls out from the algebra. The algebra suggests that there's also an option when b is 1. Well, if b is 1, then a is going to be 2. And if a is 2, then we have this point because, well, I can plug 2 into f and I get back 4. So I have this point 2 comma 4 on f, and I can plug 1 into g, and I get back something. I get back 0. So actually, there's this point 1 comma 0, and let's see what else. I can take the derivative of f at 2, and I can see what I get. The answer is I get 4. And I can take the derivative of g at 1, and I get also 4. So, alright, what is this line? I hesitate to draw it because it's going to be maybe hard to see or something, but alright, too bad. This point right here is 2 comma 4, and this point down here is 1 comma 0, and that looks about right, that there is this other line passing through 1, 0, and 2, 4, which is the tangent line to the graph of both of these functions in the other way. And, of course, if you use delta y over delta x to compute the slope of this line, then you get that I'm going to go certainly up 4 and over 1. So, indeed, the slope of this line is 4, and I've already checked that the derivatives of the derivative of g at 1 is 4, and the derivative of f at 2 is also 4. So these are this purple and this blue line are the two lines, and the final thing to do is to write the equation of that line. Let's see, what is it? Well, it goes through 1 comma 0, so it's like y equals 4 x minus 1. So you can just leave it like that, or you can write it as 4x minus 4. So one of my lines is 4x minus 4, and the other one is y equals 2x minus 1, and that's problem number 73. Goodbye.